Hello and welcome back to Calculus 3. So the section on 13.2 on double integrals over general regions. So last time we talked about rectangular regions where the region over which you integrate is a rectangle, right? Or square is a special rectangle, right? So rectangular region, and that meant that your stencil that you use to cut through the surface Z is rectangular, and you cut down the piece all the way down to the XY plane, and you can find the integral, right, which will give you the volume for that object. So in 13.1, why is this out of order over here? There. There. So in 13.1, what we did is we said that our region R is a rectangle. So that rectangle might look something like this. On x-axis going between a and b, and on the y-axis going between c and d. And we had the integral, let's say a, b, c, d of fxy, and then we had to do dy dx because we put a and b on the outer integral. Now we also said that you can swap the order of integration, and if you swap the order of integration, you can have c and d on the outside, a and b on the inside, fxy, and then you have dx dy, because now dx is in the inner integral with the a, b, and dy is on the outer integral to match c and d. Now, another problem I did with that rectangle integrating, and I showed that at one point area between two curves and the double integral without the function inside was one and the same thing. And there was that one particular step that was very interesting. Let me find it here. This step here, which matched exactly the setup if you use the formula between two curves. Now that is going to be the driving thing today for us, to actually move from rectangular region into the general region. So what I'm going to do now on the inner integral, instead of having the numbers as limits, I'm going to have functions as limits, allowing for different functions to be in the domain. So now in 13.2 we have general region R, which could be, let's say, two parabolas intersecting, right? So you are going to have the parabola f on top, g and h, sorry. So g on top and h on the bottom, right? So those are functions of x and y. Sorry, no, those are functions of x, not x and y. Functions of x. And now if you take a look at this, you know what you can do, right? You can look at that region and say, okay, so my x's are between a and b, right? That's left and right. So if you are using Calc2 area between two curves, you can set up the integral area of a and b, and then you have f of x minus g of x inside the parenthesis, and then you have dx. But we shown yesterday, right, that what you could actually do is you can have these. So let me write that here. We can have these as limits in the limits of the inner integral, limits of the inner integral. Because, as I said, when we go back to this problem, you see that the inner integral here spawned this part, which was actually the difference of two functions. So we can get the inner part, right, the f and g, sorry, these are supposed to be G and X. G and H. G minus H, upper minus lower. Upper minus lower for us. So G and H. I'm teaching Calc 2 as well, and it's just F minus G in Calc 2, but over here we keep F for the main function that we will integrate eventually, so the limit functions should be G and H. So, as I look at this with my Calc 2 eyes, right? When we look at this at Calc 2 eyes, I have my A and B as limits of integration left and right, that's X, and then I have G minus H, top minus bottom, to give me the inner. So this is the standard, I believe was a 6.2 setup for from Calculus 2. But now what we say in Calculus 3 and looking at what we had before, we know that this G and H can go into limits, and then we are invoking another integral. Now, you know, a lot of people would say, well, why would you make it worse, right? You had one integral, now you're making it into two integrals. Well, if I do this, I am still free to put a function in here, which is something I couldn't have done before. You see, so if I'm using the Calculus 2 version to calculate just the area of this, right, I am stuck with the area on the 2D plane. But if I ship these subtraction, right, as f of b minus f of a, if I ship that into the limits of another integral, then I have this freed up inside the integrand, which means that I can actually now have a shape on top of it, and I can use it to calculate volume, because 1, 2, 3 dimensions, right? It's volume. So now, when we have a general region, we can find, and this is the now official formula for volume, the integral a, b, and then integral h of x and g of x, and then f of x, y inside, and then we put over here, it has to be dy dx, but then there is another form that we can have with a c and d, and h of y, and g of y, and then again function of x and y over here, and then dx dy. So you have two flavors, right, whether you are going to do the y or the x. And this would be our, now clearly we can just go and say that all of this collapses into a double integral f of x, y, dA again. And then the situation will tell you, if your domain is rectangular, then all of your limits are numbers. If your domain is general region, then the outer limit is always numbers, and the inner integral limits are always functions. So with this in mind, we can do more work, right, and integrate more stuff. So if I want to find the volume of this mouse, for instance, right, you see that its base is not rectangular, right? The base are maybe parabolas or whatever, they're curved. So I'm integrating that kind of shape because that's a stencil, right? And then you have the surface of the mouse, which will be some kind of a z function. So I will use x and a y, and then whatever the functions are. So the way I'm doing this, guys, is I'm tracing this mouse on a paper. When I trace this mouse on a paper, I see what functions fit through the trace on the paper. And those would be your g and h functions. And then you have, you know, whatever you're using, a or b or c or d. And you can then take a look at the surface and figure out what type of a function is this, maybe or some kind of cylinder, definitely, right? And you can come up with the equation for that and figure out the volume of the mouse. Now, volume of the mouse is not something that you actually need when you design these things, but we talked about interesting architectural shapes that are not just boxes like this room where you can multiply 3 dimensions and be done, but, you know, certain awkward buildings and things that are there with architectural design. You need to know volume, as we discussed yesterday, because of design of heating and air conditioning, which needs to be designed carefully once you know the exact volume that needs to be heated or cooled. So figuring out the volume, and obviously, guys, all of you who are mechanical engineers and structural engineers and all of that kind of stuff, this is something that is very, very important because you deal with volumes at all times. So, believe it or not, that's it. The only thing that I have to really write here and write here in blood is that you cannot simply switch the order of integration. That is a no-no in 13.2 and for the rest of this chapter. So you are free to switch order in 13.1, simply swapping dy, dx, and the limits. You have the same answer all the time. But for this, no. I mean, common sense should kick in immediately that if you just swap these two and put the functions on the outside, you are no longer coming up with the number for an answer, right? You will come up with the answer that will have x in it, and that's not a definite volume. So first thing is there. Now, there is a way to switch the order of integration, but that is going to be much more involved. So over here, I'll just say it is not trivial to change the order of integration. There we go. All right, so let's go and solve problems. First, we have what I call the vanilla problems, the basic problems, where you simply just solve whatever they give. They say evaluate integral, and they give you about 12 of these. So you are just supposed to solve stuff. I will work on 2 of them. So let's go with 20 and 22. So problem 20. Problem 20 is 0 to 3, and then integral of x squared and to x plus 6. And then we are integrating x minus 1, which is a plane. And then we have the order dy dx. The most important skill that you must have here is how to draw the domain looking at the integral limits, and also how to come up with the limits once the domain is given to you. That is the only skill that helps you set up the integrals or change order of integration if you have to. You will have to change order of integration if you run into a problem that you cannot integrate, let's say in a dy dx fashion, but you could integrate in a dx dy or dy dx, whatever is the other one, whatever. So even though it's not required in this problem to know what the domain looks like, you better be able to come up with that. So how do we do that? Well, first off, you realize that the inner integral is wise, okay? So if the inner integral is wise, your limit functions are y equals x plus 6, which is a linear line. You better know how to graph that. And y equals x squared, which is the basic parabola. You better know how to graph that as well. So now you will draw the domain, and you will have the exact picture of what you are dealing with, right? So x plus 6 and x squared, that's all above x-axis, so we're going to draw x-axis all the way down. We know that for our parabola, 0, 0, 1, 1, and then 2, 4, and then 3, 9, so 5, 6, 7, 8, 9, and then the other points are symmetric. If you are not using square paper, I have no clue why you're sitting in this class. And then we have 1, 2, 3, 4, 5, 6 for the linear line with a slope of 1. So now I have my parabola. When I connect the dots, this is just like a coloring book, right? When you connect the dots, you don't have to color. And now you will draw the linear line slope 1. There we go. And if you look at this, right, you have your region R. So whatever is in here is region R. So you will always look at the limits of the integral, pull the functions down. Now, oh, sorry, I made a mistake. I made a terrible mistake. We were not done. So we did put the two functions together, and then when you look at the first integral, it says that you're cutting your x between 1 and 3. 0 and 3, sorry. So the only region that you are considering is actually this one. You're not considering the other side at all. You are only looking for the volume of the object that is cut out with this stencil, right? So this is the shape of your cookie cutter that cuts into the x-1 plane, and it cuts something that it's this shape. We can find volume by simply solving the integral. That's not an issue, but you know, 90% of this lecture for you, if you want to work, is actually dealing with what I have, and that's pretty much it. The rest you can punch into a software and it will give you the number at the end. The software cannot come up with this integral looking at the picture. That's what the software cannot do. Maybe, you know, give it another 20, 30, 50 years, maybe. But right now, the only job, the only thing that you can make money with if you are going for this type of stuff is you staring at the picture and writing the integral. And that's it. If you can't do that, you are useless to the job position, right? Because integration is irrelevant. Computer does that now. Let's integrate. We are integrating the inner integral. Inner integral has x-1. We're integrating with respect to y. So we are getting x-1 times y, because x-1 is a constant in eyes of y. So it's pretty much like integrating 7. So you got 7y. Right? That's pretty much what it is. The limits are from x squared to x plus 6, and we still have dx to deal with. So now we have 0 to 3. We have x-1 that multiplies y, which is x plus 6 minus x squared. Dx, now we do algebra here to see what the polynomial is that we need to work with. So we have x times everything, which would be x squared plus 6x minus x cubed. And then -1 times everything. So that's minus x minus 6 and plus x squared dx. Simplify, integrate, and done. So we have negative x cubed plus 2x squared plus 5x and then minus 6 dx. And now we're finally integrating that one for negative x to the 4th over 4 plus 2/3 x cubed plus 5/2 x squared minus 6x between 0 and 3. We are only computing at 3 because minus 0 will kill all of the terms. Again, there is no plus c. This is a definite integral. This is negative 81 over 4 plus one of the 3's will cancel the denominator, so you have 9 times 2 is 18. Then we have plus 45, that's 9 times 5 over 2, and then minus 18. These guys drop, and all we have to do is, this is 9 over 4, obviously. All right, 45 doubled, right, to get you a quarter is 90, 90 minus 81 is 9. So 9 quarters. 9 quarters is what you have as the volume of the object that you cut below the plane. So now, you know, in all its silliness, what do you have? You have x minus 1 plane, which is your cookie dough, and you came up with this stencil, and you pressed into that slanted cookie dough with a stencil, and this crazy cookie has this shape on the outside. It's flat on the bottom because it stands on a desk. It's flat on the bottom. It has this on its sides, and on the top is cut at the x minus 1 slanted plane. That's the shape. Great. Would you like to have that cookie? Oh, I would. Yes?
How would it be positive 9?
I'm sorry?
How would it be positive 9?
45 times 2 is positive 90, right? 90 minus 81 is positive 9. Yes?
Wait, is the flat surface the area in red, or is it coming up?
Yes,
or
yes.
Is it like
very good. Flat surface is on your desk. This is the shaded. So this is the area of your desk, right? So when you draw this in your notebook, this is exactly what the base is.
Are you looking at from?
And the object builds on it.
Oh, okay.
The object. So this is right. What is the shaded red? Shaded red is this surface of the mouse. Okay, and then these walls will rise up. Will rise up, right? Up, and those are the walls of the mouse. And then this shape on the top is x minus 1 cut, which is the plane. So that's the x minus 1 plane over here. These are the bounds, and those bounds go straight up because your cookie cutter stencil went right back down, right? So it made the perpendicular cuts to the desk. So how big is your shape? On sides is how big this is, right? Because that bounds, right? That's the region over which the object exists. So that would be the bounds of the printer, the bounds of the classroom, the bounds of the tree, the bounds of whatever 3D object you are considering. We will do much more of this, obviously, and especially for changing the order of integration. But this problem did not require this at all. But when it's so simple and quick to do, why not? Now the next problem is one of my favorites. Because we're going to utilize IQ rather than power. What you have here is 0 to 1, from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And we are integrating 2x squared y dy dx. Sheesh. Huh? I love this. What is your base here? What do you think? What's the base? What's this shaded red region? What are these square roots? What would I give you? What is that? No, it's x squared underneath. It's not a square root, x. It's square root of x squared. What is that? Well, you don't know until you write it on a side that y is equal to square root of 1 minus x squared. Then you do what? So what is this? It's a circle! Nice! So this is a circle because when you square root both sides, you get x squared is equal to 1 minus x squared, and then you move x squared to the other side. This is a unit circle. You are integrating over circle. But it's only half of the circle. Because your x is not going from negative 1 to positive 1. It's going from 0 to 1. So you are integrating only over half of the circle. So your domain, your stencil, is half a circle. So this is the base for your cookie now. The surface, the wavy surface of the cookie, or the top of this mouse, is given by 2x squared y, right? And you have your domain. So this is good. Now let's do the integral. Observe that you are integrating y, right? Y is the first one to be integrated because the first integral is dy. So as you integrate that, it will be y squared over 2. That's going to kill a 2 there. So you just have x squared y squared from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And you still have this dx at the end. 0 to 1, x squared times x squared on the top. X squared will kill the square root, and you get 1 minus x squared. Minus the 1 on the bottom, the square will kill the negative. So try not to put too many negatives here because they're not supposed to be there, right? This minus sign over here is getting killed by square on a y. But this minus sign exists because of the formula. It's f of b minus f of a. So we don't get to count this negative. That negative is out because squared is killing it. This must remain, obviously, because it's there from the formula, and there's nothing to counter it. So that's a little bit of algebra, which I really shouldn't be covering, but we all know I'm the best. So now what do we have? 1 minus 1 is what? 0. And negative x squared plus x squared is 0. What now? Is this just going to be 0 for the end? You integrate 0, you get 0, and you have nowhere to plug these values. So, Sorry? Well, representative rectangle is dx, right? And it spans. We are going to actually learn the representative rectangle in the next example because as you draw, you are just supposed to solve this, right? This is just supposed to be an exercise in figuring these things out. So what might be the problem over here? Yes?
You should have to like separate the, make it like 2 angles instead of 1. So there's one from negative 1 to the positive side. So instead of going from negative square root 1 minus x squared, we do 2 times integral 0 to square root 1.
That is a very dangerous business to do. Yeah, I would agree, but see that the trick is that the symmetry is not guaranteed on top. You see, for areas, that's cool because you see everything that you're doing. But you have to agree that if I cut this mouse halfway this way, there is more volume on this side than on that side because you see it's fatter here. It's symmetric this way if you cut, but it's not symmetric that way if you cut. So the playing the symmetry card in Calculus 3 double and triple integrals is extremely, extremely dangerous business. Because on the top, right, when you have a slanted, so let's just build the shape underneath, right, with the straight walls going down. This is clearly a rectangular integral. If I cut it this way, the volume on this side is bigger because the slant goes that way. Your area on the bottom is cut perfectly in half. Just like over there, the 2 quarters will be cut in half, right? So this is cut perfectly in half, and on the area-wise, but the volume-wise is not cut in half because there's more stuff on this side than on that side because it's slanted top. So now when you have the wavy top with sines and 2x squared y's and so on, there is no guarantee of a symmetry unless you are working with the shapes that you know 100% are symmetric, like elliptical paraboloid, right? Elliptical paraboloid is a nice round, right? And it's right, so it works great. So guys, for problems like this, changing the order of integration might be something that we would have to look into, right? In which case you would have to write the two integrals. So when you look at this problem, right, we integrated out y. That was our job. We got y squared over 2. 2 and these 2 canceled, and we just have x squared, y squared. When you plug in the square root, right, you square it. It just loses the square root. On the second one, when you square the whole thing, the square kills the negative and kills the square root, but you are left with a minus sign. And that minus sign, what it's going to do is going to tell you that, right, when you do the subtraction over here, 1 minus 1 is 0, and x squared plus x squared is 0, giving you 0 on the other end. The value of the integral is 0. Is the volume 0? No, right? There is a shape there. So we have to learn more. We have to learn more to fix this. You've seen these issues before in your education when I asked you, if you were not in my class for Calc 2, someone asked you to calculate the area under the sine graph from 0 to 2 pi. Right? And if you go 0 to 2 pi of sine x dx, you get 0. Yet you know it's not 0 because there is the area that you can shade. The area is 4. Right? So because of those kind of things, right, we learn how to change order of integration, and we also learn how to come up with integrals by looking at the shape that we have. Step number 1 for any one of these things is going to be figuring out the formula that is there for you to work with. So usually there are mice on this that are detached. Are there any mice that are detached with all the things on it? Oh, that's okay. Like, this one was pretty much always detached, but now it's attached, obviously. They're all attached. Do I have a shape? I don't have a shape. Whatever. I'll say the words. So what are you doing now? I have a shape right here. Right. So if this is a stencil, right? So if this plastic object, this is the cover for one of these desks. If this plastic object is the stencil for your cut, right? That means that the shape will build on top of it. You trace that on the paper, and then you figure out which functions describe this, and those are your g and h functions that go into the integral. So, evaluating integrals where the region is given, and they only, I don't know why, like the most important stuff is always missing in these textbooks. They give you only 2 problems that are actually important, and then, you know, another 100 garbage problems that make no sense whatsoever. But here they are, problems 31 and 32. They give you graphs, and they say, give me the integrals, right? And these are really good, especially the one with the circle, right? That it's cut at this awkward angle. Because this is what your parts are in mechanical engineering. This is what the architectural buildings are, the structural, right? You talk with bridges and all these kind of things. They're not done at the right angle like this boring room, right? Anything that is new and nice and designed, right, has curves and has angles and things like that, right? So when you look at these, right, how do you set up the integral for the region? And I'm going to discuss both of these problems in great detail. and then just challenge you to go online and find more of these problems, or draw your own problems, because whatever you draw, right, if you can figure out what the function for that is, you should be able to set up the integral for the object that lives on top of that. So these are the domain stencils, and I'm going to start with explaining 31 in detail. So we have two linear lines intersecting. So one is y equal 2x. And the other one is y equals 3x minus 9. So it cuts out this triangle. And now in this triangle here, I'm supposed to set up the integral over, so this is my region R. I'm going to lightly shade this and say that's region R. Now, when you are setting up the double integral, we always say it's the integral over region R of f of xy dA, right? So, when you put the picture together and you know that that's your region R, you have to figure out the volume that is above that when this is given. If this is not given, then it's just the area of that triangle. Okay, here is the big deal, and if you understand this, the rest of this chapter will be a joke. And I'm not joking about that. Your realm now is 3D. That means you have a two-dimensional input where x and y dimensions are equal in terms that they are both independent variables, input variables. You know that this dA could be dx dy or dy dx. You further know that whatever your outer variable is, its limits will be numbers, and whatever the inner one is gets the functions. You also know that when you draw a representative rectangle, the edges of the representative rectangle, whether it's horizontal or vertical, these edges have to ride the same function the entire time for the duration of one integral. Now that is the crucial piece of information for you to set this up. When you look at this problem, to set it up dx dy or dy dx, one of these will have one integral, the other one will have two. And these are the things you have to be very careful about. How do you know which one to pick? Which one is less work? Sometimes one of these is not even possible. We'll see that as well in the next example. But in this case, you can set up dx dy or dy dx. However, one of those two will be half of the work, because one will be set up as two integrals and the other one will be set up as one integral. Now look at this. If I draw what we always are used to, the representative rectangle dx, observe what the top and the bottom of that representative rectangles, which function they ride all the way throughout the integral. You see the top always stays on 2x. Do we all see that? But look at the bottom. It's riding the x-axis up to this point, whatever this point is, and then it swaps and it rides this linear function for the rest. This is where you have two integrals, because you see that the dx hops the function, right? It goes from function y equals 0 to a function. So that's the lower integral, right? Lower limit. Lower limit changes after this point here. And that's a problem. Well, it's not a problem. It just sets up another integral. So if you want to use dy dx, that means that the dx is the main representative rectangle, and the dy will be top and the bottom of it, right? Because those are the functions in the limit. If you are to use dy dx setup, you would have to say, okay, double integral, this point over here is 3. So your double integral would be whatever f is, right, dy dx. So dx on the other side, you see that it only goes from 0 to 3. And the functions, the bottom function is 0, and the top function is 2x. And that only covers up to 3, up to here. Representative rectangle will move past 3, but that adds another integral, and now it goes from 3 to this point over here is 9. It's going to go 3 to 9, and now it's writing 3x minus 9 on the bottom and 2x on the top of f dy dx. So I had to set up two integrals for this situation because the bottom of the delta x, swaps the functions, as you can see, is 0 here and it's 3x minus 9 in there. That's why you cannot have a single integral, because you can't have both of these at the same time. Now, if you want to set up a dy integral, in this case, much better, only one problem to solve. Because dx dy integral is forcing the horizontal representative rectangle. And if you are having a horizontal representative rectangle, do you see that in this particular case, horizontal representative rectangle will swipe on the bottom to the top, where the left and right sides always write the same function? Do we see that? So that's why it's a single integral. So it goes from the 0 level to the level of 18, because this point over here is not 3, 9, it's 9, 18. 918 up there. So you see that your outer limits, right, your dy limits, are from 0 to 18. And now the inner limits are x. So this has to be x1 and this has to be x2. But what you have is y equals 2x, from where x is equal to y over 2. So that's the upper limit, y over 2. And you also have to figure out the bottom. So that's 3x minus 9, from where x is equal to y plus 9 over 3. So y plus 9 over 3. So these are the two integrals that you can set. If you want to go dy dx, you would have to use two integrals. If you want to go dx dy, you get to work with one integral. And that's for the shape that you see up there. Every shape will be unique, like this. And you have to figure out which way you're going to go through this. So now I'm going to go through this argument one more time to make sure that you at least get some of this, and then we'll go on and so dx is the vertical representative rectangle, and as you draw a dx over here, you see that the bottom of that dx is going to go on the x-axis and then hop on this function. So the bottom changes. So that's why we have two integrals. So 0 to 2x, because the bottom is touching y equals 0 and the top is touching y equals 2x. So those are the inner limits. And then when it hops here, the bottom is touching 3x minus 9 and the top is still touching 2x. When you have a vertical representative rectangle, you see that representative rectangle is always writing 2x on the top, and there is 2x and there is 2x. Your dx is going from x1 to x2, so for the first integral it goes from 0 to 3, dx goes from 0 to 3. For the second integral it goes from 3 to 9. because it covers this region here, right? It's right there. So delta x covers all of this, which is 3 to 9. So we need two integrals to set up dy dx string. If you swap and you want to use dx dy, then that's going to be one integral because the left side is always on the 2x function and the right side is always on 3x minus 9 function, which allows us to have one integral, but you have to switch those functions because the inner integral is now x equals function of y. So that's, that's something that you have to be careful about. So this was an exercise for you to understand how to get from the picture down to which order of integration is easier, which order of integration is less work, and so on. But you also, as a free gift, you also got the instruction on how to change order of integration. You see it's dx dy over there, and it's dy dx on the other one, right? This is all of the work that is required for you to switch the order of integration, which is the reason why I wrote earlier, it's not trivial to swap dx dy in 13.2 and beyond as if it was 13.1, where you can just switch it and switch the limits and you're done. Rectangular regions are a joke. These guys, as you can see, not a joke. So this is the first exercise. Now let's go take a look at 32. 32 has this half a circle that it's intersected with a line. So here's my circle, and the xy axis are cutting right through the middle, and then we have this line, and our region is right here. The circle is radius 5, therefore this equation here is given as y equals square root of 25 minus x squared. And the linear line is given to us as y equals negative 3x plus 5. Now, since book really likes to, encourage the learned helplessness, they also provided us with this point. Trust me, I will never do that because I have high opinion of you. And I know that you are able to set two equations to each other and find that point like you always did in the past. So, since I think highly of you, I will not provide this point, right?
Thank you.
And you can write the strongly worded letter to the author of the book to remove that thing from there so that you can, right, figure your engineering out at a better rate. All right, so we are looking for the, again, integrals. So we're looking for those limits. And this is one of those situations where one of the possibilities cannot be used at all. Can you tell me which one cannot be used at all? Is it dx dy or dy dx? Keeping in mind that whatever is the outer one is the only representative rectangle you draw, right? And then the other inner thing is the top and bottom or left and right. So which one do you think is not possible to set up at all, and why? Why?
Because it's going to equal, it's not going to come out right. It's like below the 0 line, below the x-axis. It's going to shade into each other, so it will cancel some terms out. It won't equal exactly.
I'll keep my poker face without saying right or wrong. Let's see if more people want to chip in. What do you think? What cannot be used?
The dy dx.
Someone giving breakfast. Oh my God, I can't hear. What?
Dy dx.
Okay, why?
Uh,
Martha, you have to be cooking and bringing every day now. That's, you only have 2.5 weeks left, so. Oh, food is coming. dy dx, you said?
yeah, because I think it was a rectangle parallel, not perpendicular to the x-axis. Then it means that you have two equations because
Well, I didn't say break into two equations. I said not possible. So there's a difference. What do you think?
Well, if you when you do a vertical rectangle,
dx?
slide it across. Once it gets to the point where the 2, -4 past that, you'll be doing it between the two, like two parts of the same equation.
And that kills it. That kills it. As soon as you draw dx right here, you see that it folds on itself. It's the same function on the bottom and the same function on top. That's immediately going to kill it. Right? Which is the problem we had earlier when it folds on itself as we use dx, right? You see that? It cannot be computed. And that's the issue we had. So that problem returns a 0, but it's a false answer because you are not allowed to set up integrals that way. So the only option you have in this case is this, and the other one has to go. Has to go, and I'll draw the circle here, and then I'll draw this dx part, and I'll just circle here and here, and that should be enough, right? It should be enough to explain that it is a problem, because the upper limit and the lower limit will be the same function. And what happens when you subtract the same function, right? Right, you always get the 0 there. So we cannot use this one at all. This problem has to use dx dy. It has to use dx dy. So we are setting up the integral over region R for our function f dA in sense region R of f, and it has to be used dx dy. So now we are going to look at the picture and just write the integral out. So f dx dy. So the y. Clearly the lowest point for y is -4, and the highest point for y is 5, because that's the radius of the circle, and the top over there is 5. So your representative rectangle, which is now horizontal, will start at the level of 3, -4. So -4 is the lowest point it goes, and it swipes all of the y values all the way up to 5, and it stops. Again, the outer integral must correspond to the outer variable. I hope you all have boats to go home. Now, or a scuba gear or something, which is, right? I can't even see the trees. How much rain. You park so far away. See? I'll give you the ride to the car if you stick around. All right, so now the inner integral here, the red one, right, is x. Guys, this is one of the major issues you have collectively on the exam. The inner functions are x and x1 and x2. All right? X as a function of y and x as a function of y. So what this means is when you start measuring from the origin, function that it's furthest away, your g, your top, minus function that it's closer by, your h, your bottom. That's what it is. You learn this by far minus close. Far minus close. So I've seen students actually sometimes on the exam, they, instead of writing the proper mathematical notation, they put close and far. Because actually those two words work whether you have dx or dy. It doesn't matter, right? Because one function is further away from the axis and the other one is closer by. So close and far, and I see that on a test, right? Sometimes students write over it, sometimes it's erased, but I can still see it. So that's the deal. But the most important part here also is to understand that the function has to be in terms of y, and none of these are given to you in terms of y. So you have to massage both of these to get y x equals in terms of y. So now, what is the bottom function? The bottom function is the one that it's close, and that's the linear one, right? So now you take your linear function, which is this, and you go y is equal to negative 3x plus 5, y minus 5 is equal to negative 3x, x is equal to y minus 5 over negative 3. You can get rid of the negative by swapping the order. So this is 5 minus y over 3 if you don't want to drag that negative. So that's the lower one, the closer one to your y-axis, because you are dealing with dy. Now the other one is luckily symmetric, right? Because it's the equation of the circle. So these just get swapped, and you get that. So this becomes the square root of 25 minus y squared. And there's your integral. Now, what you have here, I'm just going to say here in green, use all of this to fix problem 22. And then just do it. There we go. So this is what is involved. Now, just one of the instructional things, you should know this, but then I can't really gamble on it. Over here, I'm going to cut my circumference in half on a horizontal, label the top as y equals square root of 25 minus x squared, let's say, and the bottom as y equals to negative square root of 25 minus x squared. The bottom circle, I'm going to actually move it in a center here. The bottom circle I'm going to cut vertically for dy, and have this side to be x equals square root of 25 minus y squared, and have this side over here to be negative square root of 25 minus y squared. When circles come up, you know, sometimes awkward things happen, and then, you know, if I'm not laughing, I'm crying. Middle school, okay? So the top and the bottom halves, they have formulas in terms of x, plus and minus for the top and the minus for the bottom. Now when you have the cuts for dy, and these are usually the ones that are wrong, make sure that the right half is x equals, and then in terms of y, the negative is on the left to compute, because we are going to use a lot of these as we move along. So that's that. All right. So what we have here is one more problem for you to enjoy, and then we are going to work on the review. So let's pick some of this. What's good? Ooh, this is perfect. Problem 50, you're going to love this. It says evaluate the integral over region R of x plus y dA, where R is bounded So BDD bounded by y equals absolute x and y equals to 4. This is so awesome. Draw the domain.
I'm getting a phone call from California selling marketing something. If they call again during the class, I just want to ask, preferably a female, to just answer the phone and say that I died. That way they start calling. Like, no, he passed away. Yeah, 2 days ago. I'm sorry. Oh, now I'm getting phone calls from that. Political correct. Correct.
All right, so let's discuss at least the domain. You are supposed to draw this, and then once you draw, it should be immediately clear what to do. So the absolute value function are the 45-degree lines. So it's a V shape. And then we go at elevation 4 and draw a horizontal line, creating this triangle. This triangle is actually a right triangle with a right angle on the bottom. It's not important, but you know, it's cool to know and realize that. So we have a linear line intersecting with this triangle. And now we are going to we have our region, right? So let me shade this. So this is our region. Now, I have a choice between dx dy or dy dx. And that's the first choice I have to make. Now, both of those choices are viable because you have three functions. Even though the absolute value function came as a pair, these are actually two separate lines. One is y equal x. The other one is, so this is y equal x, y equal negative x, and y equals to 4, right? So I have these three different functions. So since there is no circle and a parabola and things that bend back on itself, right? We're not going to run into a situation that we cannot use one of these guys like in the previous case. However, it should be clear that one of these two will give you two integrals and one will give you one. Now, as you draw your dx representative rectangle, and technically you can't do anything in this chapter without drawing dx or dy, so get used to it. And as you let this slide to the right, it should be clear that the top always rides function y equals 4, but the bottom hops the function, right? It switches from negative x to positive x. That means that if you are using dx as the main representative rectangles, you will have two integrals. Now, if you're using dy, which is the horizontal one, you can see that the left side is always going on a negative x and the right side is always going on a positive x, all the way from the bottom, all the way to the top. So this is going to be one integral. And this is my choice because it's less work, right? Mathematics is all about being lazy, which is why we generalize so much. Right? You have multiplication tables because why would you go 3 plus 3 plus 3 plus 3 plus 3 if you can memorize 3 times 5 is 15? Mathematics is all about being lazy as much as possible. So we know that the dx dy will give us one integral, and that's the one we set up. All right, so now that you know that much, set it up. And let's see what you come up with from there. What are the limits on the outer integral? 0 and 4. Very good. And how about inner integral? That's not a rectangle. Yes. The left side is writing the function y equals negative x, but it needs to be x equals y, so x equals negative y. So that's that. And now we can solve this. So 0 to 4, we are integrating in respect to x, so we have x squared over 2 plus yx computed from negative y to positive y, which plug into all x locations. So 0 to 4, and now I have y squared over 2 plus y squared minus y squared over 2 plus minus plus y squared. There we go. dy. These guys cancel. And I am integrating now 2y squared. So integral 0 to 4 of 2y squared dy, which is 2/3 y cubed from 0 to 4. 4 cubed is 64, so 128 over 3. So the volume of this object would be 128 over 3. Again, it's under the plane x plus y, so it's a plane, and we have it. You just let it go at this point. I would label that as the helium-induced singing. Is that what it is? Some of the cool images and other problems that you can consider. You see on the top that wedge, right, is has equation z equals 2 minus y. On the bottom, you are looking at a quarter of a circle, right? So that's a problem that can be solved either dx dy or dy dx just by looking at the arrangement. Now, obviously, you will be practicing that. Going further, problem 71 is the paraboloid. So finding the volume of it. You are integrating the function z. Your domain is given by intersecting the functions. You see that the circle with radius 3 is what your domain is when you are writing the equations. So you'll have those square roots going on. And then this solid, which has a parabola. What you're doing is you are shining the light above the object to cast a shadow on the xy plane, on the floor, and that shadow is your region R. And the outline of that shadow are the functions that go into your g and h limits. So quarter circle on the top, full circle on the in the middle, parabola in the straight line on the bottom. You also see that for 72, the bottom problem, you are not able to use the integral that is dx dy, because dy is folding on itself, right? If you draw a dy representative rectangle, it's touching the same function on both edges. So that's going to give you 0. So yes, you can cut into two integrals. You go from one edge to 0 and then from the other one to 0. But again, why complicate things if you can just quickly do dy dx integral, which would be a single integral and solves the entire problem, because the bottom of dx will always ride the parabola and the top will always ride the straight line. So that's the quick fix and quick solution to it. And then the bottom two problems, you have the whatever crazy shape. We really don't care what the shape is on top, because that formula is given to you, right? The only thing you worry about is what kind of stencil is used to cut through that object and give you the volume. So that's that. And over here you have the trapezoid region. So clearly you are going to have, if you are using dy dx, you're having one integral, but if you're using dx dy, you're having two integrals, because you have a rectangle plus a triangle on the cut. All these shapes, I mean, you know, it's up to you to sit and figure out these calculations. And yes, we are going to send this immediately onto the triple integration. When you take that Z shape, which is the top, and you say, well, the bottom shape doesn't have to be 0 now. It can also be some kind of thing from the bottom. So now it's top minus the bottom, and you put that in the limits, and you're allowed to put the fourth dimension now inside the integral, and then you can talk about distribution of temperature, you can talk about the density, you can talk about all of the things that can happen within the 3D object that you can pick up, because you can use 3 integrals to describe the volume, right, the bounds of the object completely, and use the fourth thing that you put. Right, so we are now up to 3 dimensions with 2 integrals, but we can still upgrade that, and that's coming up in 13.4. So next one is still double integrals, but it's double integral polar coordinates. So for the next lecture, your focus and review should be on polar coordinates from chapter 10, right? So 10.3 and 10.2, I believe. Yeah, 10.2 and 10.3, those are the reviews for the polar coordinates for the next time. Bye.